Okay, so this is a brief video to describe how to analyze a carbon Auger peak to extract from it a measure of the sp2 to sp3 ratio of the carbon that you're looking at. Recently, us folk at Nexus, the National EPSRC XPS Users Service, have had lots of users looking at diamond-like carbon films or nanotubes or graphene, and very interested in not just identifying which elements are present, but also looking at the hybridization ratio to see whether they've got something like pure diamond in a diamond-like coating context, or pure sp2 hybridization, as you should have if you're making good quality graphene. There's not much information about this in the XPS spectra. You could have a look at the carbon 1s peak, you can have a look at the valence band, and there's a whole set of literature about both of those. But for simplicity's sake, one of the most commonly used methods is to look at the X-ray induced Auger peak, or feature in the XPS spectrum, which you can see in front of you here. And Neil Fairley of CASA XPS is about to tell us or show us how this can be effectively dealt with. The problem is that there's quite a bit of noise on this peak because it's already on a bit of a background, and unless you acquire for a very long time, you see quite a noisy spectrum of this kind. And historically, one of the ways of extracting an sp2 to sp3 peak rate hybridization ratio is to look at the differential spectrum. And I think Laskovich published this method in about 20 years ago. I think the reference is Applied Surface Science, volume 78, page 17, 1994. And he looked at a differential spectrum. But the trouble is, if you take a direct XPS spectrum and differentiate it in something like CASA XPS, you see something like this. And the aim is to look at the energy difference between the positive and the negative going parts of this differential spectrum. And unfortunately, in this case, certainly the positive going bit is very noisy. The negative going bit, you might hazard a guess as to where the minimum is, but it's still not very easy. So Neil is going to show us a method which is an alternative to directly differentiating it, which should allow us to determine this peak energy separation much more precisely. Take it away, Neil.
We're going to have a look at how to process some data so we get a better derivative than simply applying a Savitzky-Golay. If we do a simple 5-point quadratic Savitzky-Golay on an Auger peak such as this, the noise swamps the signal. So rather than just differentiating the data directly, we're going to introduce a synthetic envelope which will represent the data. Now in this case we really don't care whether the peaks are physical or not, we simply want to approximate the data. So I'm going to add a set of peaks and just simply have a sufficient number to approximate the data, and it will be the synthetic envelope that results from these peaks which will be differentiated and provide us with a smooth curve and a better approximation to the derivative as a result. So here we have one approximation based on a set of 5 peaks. So if I use the test data tab, there's a button that says diff synthetic envelope, and if I differentiate that, it will create a derivative from the data. And here you can see there was no synthetic envelope, so you just get the derivative as if it were applied to the raw data. But where there was synthetic envelope, that is to say a peak, a set of peaks sitting on a background, the result is a nice clean derivative from which we can measure the peak to peak. And to finish it off, what we can do is add to this particular process data a background with type SP, and this will give us in the area, and actually the forward half maximum, the energy difference between the peak maximum here and the peak minimum here. So that's the estimate we're looking for the D parameter.
Great. So is that, did I see the 21 point something EV difference between them? I think yes, which is reasonable. I think Laskovich called this the D parameter, and something in the early 20 electron volts corresponds to graphite, which this happens indeed to be a sample of graphite, and smaller values of D correspond to higher degrees of sp3 hybridization. So especially if you're looking at something which is graphitic, like graphene or nanotubes, which are largely sp2 hybridized, then you should see an interval between these peaks of something around 20 electron volts or higher. And you can use this D parameter to come up with a quantitative value for the hybridization ratio. So you can see that this is a much less noisy exercise than it appeared at the beginning, and you don't have to require spectra for hours and hours on end to get very high signal to noise to do the differentiation first. You can do it in quite reasonable times if you acquire the carbon Auger spectrum. Is that it, Neil?
I think so.
I think that's it. Okay, thanks, Neil.